very happy to introduce Fabio. I think many of you already know him. He did his PhD in the Federal University of Pernambuco, and then he was a postdoc here in the IIP. And now he is in Valdivia in Chile. And today he's going to tell us about thermalization and integrable hierarchies in AdS3. And please feel free to ask questions during the talk, but using the chat. So Fabio, please go on, and thank you.
Thank you, Tiago, for the introduction. Thank you, Dimitri, and everyone for the invitation. And it's very nice to talk to you again, even virtually. I hope in the near future I can see you in person. And so let me start the presentation. So today I'm going to talk about this project, things that I've been doing related to integrable systems and two-dimensional CFTs. And now I'm trying to understand aspects of thermalization in this story. Okay, so, and here you can see the Newton's cradle. So if you ever seen this, you're gonna see briefly the quantum version of this. But you see there's this ball and there's transfer of momentum. So you can see this thing going on here. Okay. And so before starting, I just would like to make some advertisement of the beautiful city I'm in now, Valdivia, Chile. So I ask you to imagine that we are in a simpler time, that we could be here all together next to the river, seeing this beautiful city. And here's the building of Centro de Estudios Científicos, the place I'm currently working. So we could be here and discussing physics. And in front of the building, there's this Foucault pendulum that you can check that actually the Earth is not flat, right? So it's actually spinning around the axis because for some reason, this seems to be some topic that people are arguing nowadays to see what's this time. But and of course, I also like to thank my collaborators and part of the story, Dima Melnikov from IIP, Ricardo Troncoso and Alfredo. And I'm going to mention in the final part of the talk, this story that we study related to three-dimensional gravity. Okay, so the outline of my talk is that I'll start with some general introduction and motivations for my work, discussing generalized thermalization. Okay, so I hope people will be happy with this part. And I hope that you can get some lessons from here. And the second part about the generalized Gibbs ensemble for charge to the CFTs. So this will be a little bit more technical, but I hope you can also follow, so think a little bit about this part. And finally, if I have time, I will discuss about the holographic realization of integrable hierarchies in 3 dimensions. I will be very brief, so I hope you can understand something. Okay. So the first part, the introduction. So it has been known for some time that there are one-dimensional quantum systems that they don't thermalize the way that we are used to describe thermalization. So there is a lack of thermalization in the systems. And here is this very nice paper on the quantum Newton's cradle that I showed the picture of the classical one, right? So the idea is that you have this Bose-Einstein condensate. So you condense these atoms, they are trapped in an optical and magnetic trap, and you can put some anharmonic potential here. And with a laser, you can split this guy into 2 parts. So you have one part going to the left, one part going to the right, and they meet in the center after some time, and they bounce and go back. Okay, so that's the quantum analog of the Newton's cradle. And here you can see this picture that they took from the experiment. So you see, of course, there are some imperfections, but it goes oscillating around. And it keeps like this for quite a long time. And the thing about this experiment is that they study the distribution of momenta of these particles. Okay, so here you see 3 examples, and here, so the description of this system in principle is the Liebig-Leininger model, which I'm not going to describe here, but there is some theoretical model to describe this thing. And there's a coupling constant. So the coupling constant here decreases as you go down, okay? And then you see the fluctuations, and there's some averages around the fluctuations. And the important thing, so you see when the coupling is smaller, so they plotted here a Gaussian, okay? So what happens is that if you let this system evolve freely, so you just remove this trap, it should thermalize to a Gaussian, okay? So that's the usual thermalization that you expect. But in this system here, you see that it doesn't follow a Gaussian. So the momentum distribution is not a Gaussian. So this is a experimental observation of a one-dimensional system that does not thermalize that the way you would expect. Okay, so it stays in this steady state for quite a long time. And there's plenty of numerical experimental evidence that several out of equilibrium isolated one-dimensional quantum systems are not described by the usual Gibbs ensemble. Okay? And these states are called pre-thermalization states because in principle, after a long time, they should thermalize, right? And typically these systems are nearly integrable. Okay? So they are very close to being integrable. And what this means, integrable, is that they have a large set of conserved quantities other than the usual thermodynamic ones. So Rigo et al., they show numerically that observables in one-dimensional lattice hardcore bosons, they can be described by this generalized version of the Gibbs ensemble. So we call GG, the generalized Gibbs ensemble, which includes all of its conserved charges. So this would be, according to this literature, to these people, the way that you describe these observables. And then there has been, after these works, have been many numerical experimental confirmations of these ensembles. So you can really describe the observables in these experiments. Instead of using Gibbs, use generalized Gibbs. Okay, so instead of just these or particle number, you can have an infinite set or maybe a large number of these charges. Okay. And this story is very much related to the difficulty that we have to describe thermalization starting from unitary quantum evolution, right? So that's the topic of eigenstate thermalization hypothesis. So what's going on? So if you start with some wave function and you have unitary evolution, you can expand in terms of a eigenbasis, of energy eigenbasis, right? And you have the coefficients. And if you calculate the average of some observable, you get these two parts. So we divide the part that the energies are different and this part that the energies are equal. Okay. So if we further assume that there are no degeneracies, which is a reasonable assumption if the system is not integrable, and you take the long time average of this thing, it should simplify to the diagonal ensemble, which is this one here. So you see this long time average, which in the classical picture, we would relate this to ergodic theory, and it should explain thermalization with time averages. So in this simple example here, we don't get a thermal ensemble, right? And you see explicitly the coefficients that define the initial state. So this ensemble keeps the memory from the initial states via these coefficients. So the idea of the eigenstate thermalization hypothesis is a way to assume something about these averages here, so these matrix elements, such a way that you can recover thermalization. And this would be a microscopic justification for why quantum systems thermalize. And there's some inspiration by quantum chaos that I'm not going to describe here. Okay? But this was proposed by these people here, Dodge, Srednicki. And so the idea is that you simply replace, so in the thermodynamic limit, these matrix elements should be in the diagonal. They are described by some thermal ensemble. And you have these corrections here that go exponential with the entropy, right? So in the thermodynamic limit, this correction should be small because the entropy is large. Okay, so that's the ETH. But as we have seen, we have seen examples of systems that do not thermalize in the usual way. So we need another let's say, another hypothesis for these systems. And that's where the generalized ETH comes about. So if you have an integrable system, according to these authors, Rigo and other people, that you should introduce this notion of generalized ETH, okay, that you need to include all these other charges. So an equivalent statement for ETH to simplify the story is that these diagonal guys, they are described by some function of the energy, right? And then we should compare with canonical, microcanonical ensembles. But for integrable systems, we should have a generalized ETH function that depends on the higher charges, which in turn, here I'm assuming that they all depend on the energies. And then we compare this with the GG, okay? So we want to apply this to 2D CFTs. So why? So one reason that we might want to do this is because 2D CFTs can be seen as effective field theories in condensed matter physics. So for example, if you have a fermionic Hamiltonian like this, where you have some general spectrum. So for example, if you have cosine like this, so you have the Fermi surface, which here are just these 2 points, right? And so at low energies, close to the Fermi points, you can linearize the spectrum, and you have a simpler description in terms of free fermions. So one-dimensional free fermions. So like this. So it's an effective field theory description of the system at close to the Fermi surface. And because 1D is very special, everyone is strapped, so every excitation is strapped to a line. Bosons and fermions, they can be related via bosonization, so you can also replace these free fermions in terms of free bosons. And then you have this current J that should be related to the fermions. Okay. So in terms of this study of integrable systems, the conserved charges should be related to the integrable structure of 2D CFTs, whatever that is. Okay. But then the type of systems that we were talking about, this 1D quantum fluids, they are typically non-dissipative. As we saw, they can maintain these steady states for a very long time. And then these authors here, I don't know if more people also propose this, but they propose that we should include nonlinear effect to describe the dynamics when you have this type of systems, exactly because they are non-dissipative. Okay. So instead of just linearizing the spectrum, you should include higher corrections here. And they also observed that, so these guys and also these guys, that the thermodynamic limit of the Kalosher-Sutherland model, so this has been known for some time, so that they describe fractional excitations. Okay, so they, in principle, they can be simplified models to fractional excitations. And the quantum hydrodynamics of this model is described by the quantum Benjamin-Ono 2 equation, which I will explain later what this is. But so there's some hydrodynamic description for these nonlinear effects, and this system is integrable, and they are solitonic solutions, just like you see in the KdV equation, if you know what that is. Okay. So these are related. So in fluid dynamics, the Benjamin-Ono equation appears when you study deep waves in a channel. Okay. So while the KdV equation is related to excitations in a shallow channel, okay, the Benjamin-Ono equation is related to deep internal waves. Okay, so there is some physics related to these guys. And here we have the quantum versions. Okay. And well, and then these authors, they have noticed that the quantum Benjamin-Ono equation can be embedded into the CFT with a U1 current. Okay, so in these type of examples of fractional excitations, which in principle should be related to edge states in the quantum Hall effect, we should expect conserved charges related to the integrable structure of 2D CFTs with a U1 charge. Okay. And the other motivation for this work is because I have a long history with black holes, so I like black holes a lot. So I also would like to understand how black holes thermalize. So what do I mean by that? So the idea is that you start with some configuration of matter, and this configuration collapses into a black hole. And well, four-dimensional black holes are difficult, so we can do these toy models in 3 dimensions. So AdS3 is just some constant curvature space-time in 3 dimensions that you have these so-called BTZ black holes in homage to these authors here. So Banhados, Teteboim, and Zanelli, which are Chileans, right? And in particular, this guy here is the director of the institute that I'm here right now, okay? And these black holes have mass and angular momentum. They are classical solutions. But the idea of AdS CFT is that the description of this system in the bulk can be completely mapped to a 2D CFT at the boundary, which here is a cylinder, okay? So, and this CFT has primary states. So those are the eigenstates of the CFT Hamiltonian, which is expressed in terms of these Virasoro operators, okay? And the angular momentum is like this. And those are the primary states. So you see that they are eigenstates of this L0 and L0 bar. Okay. And then there's a central charge, which is the analog of the Planck's constant for us in this system, okay? Well, 1 over h bar, actually, because the semi-classical limit is when the central charge goes to infinity, okay? And in this limit, we can relate these energies here with the mass and angular momentum of the black hole, okay? But you see, so if this correspondence is correct, we can describe the whole evolution of this thing, of this collapse, in terms of CFT. So the black hole collapse is an out of equilibrium isolated quantum system, just like the ones I was mentioned before, okay? So understanding this thermalization story should also be relevant to black holes in AdS3, so in 3 dimensions, okay? But there's a literature on this story, on generalized ETH in 2D CFTs. And there's some specific assumptions that people make. So they focus only on certain fields, some operators, and the vacuum family. And also the eigenstate are some assumptions. They have to be heavy. But the overall conclusion is that the usual ETH only works in the thermodynamic large central charge limit, the semi-classical limit. But then to DCFTs, they have an infinite set of commuting conserved charges built out of the energy momentum tensor. So this is the quantum KdV charges, which I will review briefly. Okay, these people discuss it. Many other people study these, but in particular, I cite these people. Okay, so in principle, we can have this infinite set of commuting charges. And you might wonder, should we consider GGE into the CFT? So yes, so John Cardy, he studied this problem via quantum Kench, would be a sudden disturbance in some CFT initial state. And this thing evolved in general to contain higher charges related to the KdV hierarchy. Okay, so in principle, if you do some perturbation of a CFT, you should include these guys. And then very recently, these people study the generalized ETH, and they also reached the conclusion that it only works in the thermodynamic logic central charge limit. There's some details, but in the end, it should work in this case. This means that only in the semi-classical limit, it works. When you start to have quantum corrections, you have some difficulties. Okay. So the main questions of this talk, which are based on my work, is that what's the generalized Gibbs ensemble of these U1 charges to the CFTs? And do the charges obey the generalized ETH? So that's basically the main questions of my recent draft that you can find on arXiv here. And also this question related to the black holes is what's the holographic realization of this GGE? And this was actually, we studied this in 2018 with Dima and Alfredo and Ricardo. So I'll briefly mention what happens here. So I don't know if any questions on this part. So if not,
Fabio, why?
yes.
I mean, they are conserve all these charges in CFT, and if the evolution is through L0 and L0 bar,
Yeah.
why you should have a violation? Namely, why they should all only in the semi-classical limit? What is the easy explanation of this?
I don't know what's the any intuition about this, except well. So I think the most physical approach to this is this one by Cardi, that he does some quench on a generic initial state, and then he sees that in principle you should include these higher charges to describe the state.
No, this is okay. No, but you say the last sentence is
Okay.
generalized. ETH only work in thermodynamic large central limit. This is what I do not understand.
Okay. So this will become clear, I hope, in the next part. Okay.
Okay.
So I will describe what's the meaning of this.
Okay.
Okay. Thank you for the question. Okay, so now I'm going to describe the story of the GGE for charged to the CFTs. So the setup that we want, just to repeat myself a little bit, is that we have the eigenstate ensemble. So we have eigenstates with energy and charge, the U1 charge, and there's some function of these higher charges. And we want to compare these with the GGE averages given by this, okay? And we have an infinite set of chemical potentials, and the 0, 1 is just a chemical potential of the U1 charge, and eta 1 is the inverse temperature. And then you have these other ones related to the higher charges. And the partition function, so in the end, I'm gonna focus only on the integrable charges. So we can calculate the average from the partition function. So we have the partition function, and we just take derivatives of this thing, of the log of z, you can get the averages. And then we compare with this. So, and to review some essentials of to the CFT, so in this case, we have the energy momentum tensor that we expand in terms of Virasoro modes. And here you have the central charge. And the currents have this U1 guys, and they respect the Virasoro times U1 algebra. So you see here the relations, the central charge appears here. And and there's a fundamental thing that simplifies the calculations, that these guys commute, but in principle, they don't need to commute. So if you define a new energy momentum tensor like this, they do not commute. So you get a full non-commuting. So this is a technical remark, just that usually people work with a non-commuting algebra. So, but you can just see this as a change of basis. So then we define our primary states, which are the eigenstates of this zero modes. So you have this A here, the U1 charge, and I have the delta, and this VPA are our primary states. And you have this thing here. And we're gonna use these parametrizations, the Liouville parametrization of the central charge in terms of this Q, and Q is written in terms of this B. So this B is going to be our Planck's constant here. And the semi-classical limit that I was mentioned before is taken as B go to 0. Okay? And the deltas are written like this in terms of this momenta here. But it is written here like minus P squared, but actually in the end, we're gonna assume that P is purely imaginary like this. And so the integrable structure of the DCFTs has been known from the late 80s and early 90s, is this quantum KdV conserved charges that you can get from the energy momentum tensor. So this is the Hamiltonian. And then we have this next one. So it's a little bit more complicated. And then you try the next one. And then it's too big for this slide. Okay, so it's a big formula. It doesn't matter for you. And what happens is that you can show that all these guys, they commute. These are all commuting charges. And then in the semi-classical limit, if you properly rescale things here, this charge is reduced to the classical KdV charges. Okay, so describes solitonic solutions in a shallow channel. And then, but the question now is, what if we add this U1 current that I'm interested in? So what are the charges? So it happens that a natural hierarchy for this is not unique, but is the one we have the U1, you have the Hamiltonian here, but then we start to have these terms like this. So there's Tj, there's Jq, but you also have this H here, and this H is what we call the Hilbert transform on the circle. So it looks complicated in principle, but actually when you expand these fields in terms of modes, the action of this guy in the modes is very simple. So actually it's not that complicated. And you need this here because if you had just this, it would be 0 after normal ordering. So that's why you need this guy here. And you can also show that all these, the charges, the integrals of these guys, also commute. And there is also a classical integrable system in the semi-classical limit. And the quantum BO2 charges, I just showed the first two ones here. And again, there's an infinite set and it becomes more and more complicated. And these are computed with analytic ordering, and you can see a review of this thing in my draft. Okay. But I only talk about primary states, but in CFT, if you want to calculate the partition function, you need to sum over all states. And we also have the excited states of CFT, which are called dissonant states. So here, they are like this. So you just get the guys which are minus an integer, and you apply to the primary state. But then you can have a bunch of A's and a bunch of L's. So this state is labeled by what we call partitions. So you have the partition lambda and have the partition mu. There is a certain ordering of these integers. Okay. So we can simplify this notation by just defining a multi-index that includes these two partitions. Okay, this big I over here. And if you apply L0 to this guy, you're gonna get the delta plus the level. And the level is this, is the sum of the sizes of these partitions, defined like this. So, well, all this is very nice, but these guys are not eigenstates of the QBO2 charges. And if they were, it would be much simpler to calculate the trace. And what happens, and this is the important point, the technical important point here, is that we can find these eigenstates as a linear combination of these guys. So a special linear combination of these guys, you can find the eigenstates for the QBO2 charges. And this comes from the AGT correspondence. So in principle, you could find this just by trying to solve this linear algebra problem, but these people, well, actually, some other people I'll talk about now, but they use this to prove this AGT correspondence. So the AGT correspondence, I don't have time to explain details, but it's a mathematical relation between partition functions of n equal to 2 4-dimensional supersymmetric gauge theories with 2D CFT correlation functions. So there's a equality between these things, and it has been extensively studied in the literature. Okay, so it's a 4D quantity related to a 2D quantity. And the nice thing about this is that give a different mathematical expansion of these functions here that was not known before. And these people here, Alba et al.
Okay, just one question. If
Yes.
You add no charge, no U1 charge,
Okay.
the descendant would be also eigenstate of the conserved charges?
Yes. So the U1 zero mode doesn't affect this statement. Yes.
So it's just the charge which somehow scrambled the story.
So you see, if there is no zero mode, so well, what I want to say is that the Heisenberg algebra, the U1 algebra, is much simpler, right? It doesn't depend on the A's in the right-hand side.
Mm-hmm.
So, and if you put n to be 0, this is just 0. So zero modes do not affect the result of the commutativity and everything I'm saying. You can just forget about this. You can just set this to 0 and everything is fine.
So, I mean, the usual conformal field theory, no charges, I mean, no U1 charges, the descendant are as well eigenstate of all the charges you can construct. It's true, right?
Yes, yeah, like this, yes, it's
Okay,
fine.
okay. So the difficulty comes from the charge only. I mean, they mixed up the states, so this is what it does.
Well, so if you take just these guys, so what's the problem is that if you just take these guys and then you act with these guys here.
Yeah.
Okay.
Yeah.
So these are not eigenstates of the quantum KdV charges. Okay. So the problem is with this guy, actually what you get is a lower triangular matrix. Okay. So those are not eigenstates. What you need to do is you need to do some linear combination of different excited states with certain coefficients in order to get the eigenstate of this guy. You see? So
Okay.
that's a general statement. And the same thing when you add these U1 excitations, these guys are also not eigenstates of the charges, these charges like this. And you also need to find some linear combination, which here I'm writing like this. You see?
Okay.
So,
Okay. Yes.
Okay, thank you for the question. So what these guys have done is that they show that basically proving this equivalence here is the same, is equivalent to find this linear combination. And then they define an algorithm how to find these coefficients, and they find the first few ones. Okay, and that's the thing that I use. So instead of writing the trace, the partition function in terms of the trace of these bases, I will use these bases, okay, which is named AFLT in homage to these guys here, Alba, Fatiev, Litvinov, Tarnopolsky. Okay, so, and then Litvinov, later he found the first eigenvalues for these charges, but in his case, he had A equal to 0, and I just had a little bit of more work to include these guys. And if you do this work, so you can have the states with A different from 0, and you get this structure that I'm showing here. So you see, this is the eigenstate for the Hamiltonian, this is the second charge, this is the third charge, etc. And you see there is a part that's just a polynomial in P and A, and there's this other part that depend on the descendant structure. And these guys, they are actually related to the Calogero-Sutherland model because they have this structure which is a sum over the partitions. So we actually know, in principle, all these eigenvalues. So we don't know in closed form, but we know the structure. Okay. So we know it's going to be some polynomial plus some combination of charged Calogero-Sutherland energies. And these are the first few that I use. Okay. And then it becomes more and more complicated, but that's it. Okay, so we have in principle, all the eigenvalues. So now the second step, so we want to study the thermodynamic semi-classical limit. And right, so to calculate the observables, we want the free energy. And the thermodynamic limit here, we study the theory on the circle, so on the cylinder, which has size L. And the thermodynamic limit will be L going to infinity. Okay? And by assumption, the deltas, they scale as L squared, the level of the descendants also scales L squared, and A scales as L. And this is just the example what happens for just CFT. So if you have just CFT with a U1 charge, you can replace the partition function by an integral. There is the density of states by Cardy formula, and you can get the free energy. So there's a saddle point calculation, which in this example is exact, and you get this formula here. Okay. And so, but now I want to include all the other charges, right? So a further simplification is to assume the semi-classical limit. And then we are going to rescale A like this with L and B and beta, and P like this, such that delta is like this. And in the end, delta is much larger than this combination here is the central charge. Okay. And what happens is that most of the terms in the eigenvalues are negligible. So for example, here, so this is very large in comparison to this. So this is very large in comparison to this, and etc. So this disappear, this disappear. So there's a lot of simplifications. And furthermore, also these parts, the descendant parts, also disappear in the semi-classical limit. Okay. So in the end, so this is the partition function as a sum over all guys, and in this limit, it's just like this, and the L is this infinite sum of the charges. And then there's some rescale here with L to get the correct thermodynamic limit. But now I don't know the exact form of these polynomials for generic N, so I would just cut here. So I will only study these two non-trivial charges, okay, the first two guys. And then in order to have a correct semi-classical limit, I also need to rescale the chemical potentials like this. So there is a B here, because otherwise this would go as the central charge square, and this would be central charge 3/2. So, and this would go with the central charge. So in order to prevent this, I want every term to scale the same way, so I do this. And then I get this simplified formula in terms of P and alpha. And then we look for the saddle points. So what happens is that you can actually, in principle, you could exactly solve this because are quartic polynomials, but it's complicated solution. So it's better to find a perturbative solution. So we can find a perturbative solution for the free energy like this. And there's only one real saddle point, which I'm showing to you. So everything is positive if all the chemical potentials are positive. So that's why I'm showing you these formulas for you to see that all the terms are positive. So it means that this is bounded from below. So which is important if you want the system to be stable, right? And in principle, you can have a general expansion for this. The only thing that prevents us to find the general solution is that I don't know the explicit form for all the polynomials for generic K. So, but anyway. And next we can calculate the leading quantum correction for this. So now so the problem now is that when you start to include the descendants, so let me show here. So you have imaginary values, okay? But if we have a equilibrium ensemble, we don't want these imaginary parts in the energies because in principle they are dumping or some exponential increasing on the states, right? So they generate instabilities in principle. So we don't want imaginary parts in the energies. So in order to fix this, we propose so the full CFT needs the two sides. So it needs the chiral and anti-chiral, or only morphic and anti-holomorphic. So we need to include these two sectors. Okay, so if you consider the two sectors, we can have real solutions. So if you carefully do this, and then we expand, so we do a semi-classical expansion, right, around the saddle points. The first derivative is just the condition for the saddle point, so it doesn't appear. And we have the first correction like this. And if you do this computation, you get a formula like this. So in principle, you say, oh, this is just a geometric series, right? But this function, which is written here, has, in principle, can be negative and violate convergence of these things. So we also need to be careful assuming some convergence assumptions for the sum. But if you assume this, you get this form. Okay, and then the free energy is just like this. So it's the thing that we had before, plus this correction from the density of states and this type of corrections, which are like reminds you of what you get from free bosons, for example. But now you have more complicated structure. And so this is all very nice, but what happens is that if you consider only the Q2, we can actually do the computation at finite central charge. And when eta2 is real, we have this formula here, which is the exact formula. So I'm not making, so the only assumption is the thermodynamic limit. And we have this expression here, because you can sum these guys. So you can have this thing. And then you can also find a perturbative solution for the saddle point, but now exact in the central charge. And we have these definitions here for these guys, for these averages here. And this is the final result, which is perturbative. Okay, so the free energy at finite C. But this is for eta2 real. And if we assume, in principle, I could assume that eta2 is purely imaginary. And then the real part is like this. So we have only contributions from descendants. And what happens is that you can actually rewrite this part in terms of a free boson representation, and it gives this. And we derive some combinatorial identity in order to show this relation. And this matrix here is actually lower triangular matrix like this. And yeah, so, and then these guys, you can identify these guys here as partial theta functions. Okay, because the usual theta functions, they have a sum, from the whole lattice of the torus. So it goes from minus infinity to plus infinity, but these guys are called partial theta functions because go from 0 to infinity. So theta functions are nice and appear in CFT on the torus because the theta functions are these doubly periodic functions and they have nice modular properties. But these partial theta functions are more complicated, but they have some quasi-modular properties that have been studied in the literature, but I didn't do any study of this in this work. So it's nice follow-up of this work. And in the classical limit, that B is 0, this actually simplifies to this. And you see the linear free boson contribution here, but there is a quadratic correction. And this classical case can actually be related to what is called anisotropic field theories because of this type of corrections. And now the generalized ETH. So what I said from the beginning is that we want to calculate the eigenensemble. So these guys we know because this is just eigenstates, right? So we know this part. And we want to compare with the ensemble averages. So we want to see if this side is equal to this side. And what happens, so what's special of the semi-classical limit is that F is given by this. So it's just a sum of the chemical potentials and the energies, which are in the same form as the eigenensemble. So that's why it's automatically satisfied, because you just take the derivative of these and you get this thing is just equal to this thing if P is equal to P star and A is equal to A star. And by this, I mean, we need to fix two of the chemical potentials. So for generic P and A, we need to fix, for example, beta and eta. So two of the chemical potentials to be some generic value, P and A, okay? So that's the generalized ETH in the semi-classical limit. So the problem now comes in the leading quantum correction, okay? But I write here, it potentially breaks the generalized ETH. So I say this because I know that my assumptions are not the most general. So here I'm assuming still this equation here. Okay, so if I assume this, I cancel the first part, but then I have this correction here that will depend on this function, this generic function and this part. And well, I don't know how to simplify further this, and in principle, you would need to try to find chemical potentials that make this whole thing zero. So maybe it's possible to find chemical potentials that make this zero, but all the charges from K to 0 to infinity have corrections that are in principle different, okay? So you would need the same number of chemical potentials to make this zero, but you already fixed 2 for this saddle point. So we have K minus 2 chemical potentials in order to make this zero, so you don't have enough chemical potentials to make this zero. So that's my statement. Okay, so that's why I say potentially breaks. And it's similar, a similar argument was also used by these authors, Demarsky and Pavlenko and Maloney in the quantum KDV case also. But yes.
Fabio, this kind of somehow contradiction, tension you're pointing out, I think depends just on the approximation done. I mean, it's a generic problem of the generalized give things, namely, you have enough chemical potential, but when you pose the equation, the derivative has to do the value of the charges, this is a highly non-trivial equation for the chemical potential. Now, what you have done is first you have linearized, impose the condition of the charges, and then you are proving that you make correction, this might become violated. But I don't think, I mean, it's just the violation due to the approximation.
Yes.
Not something deep. I mean, sorry, I don't want to be rude, but I think it's just the fact that you have imposed this before calculating it. And then when you try again to impose it, you see, oh my God, it's violated. You see what I mean?
Yeah, no, I agree with you. So this part actually is very short in my draft, exactly because of this point that you're saying. Because I wanted to have something more concrete, and I know this is very limited assumption. So in general, I should include the B square correction like I did before also. So
just to be, I mean, imagine that you try to impose the GG really on matrices, just doing an ideal, how to say, exercise. Yeah. You invent some matrix Hamiltonian, which is integrable, blah, blah, blah. When you impose the equation that fix the chemical potential, you realize that the equation are incredibly hard, not easy at all, even in simple case. Yes. So there is even a landscape for solution. You can choose the temperature to be negative and find nevertheless value of the other one, which everything turns out to be good. So I want to say the manifold is very unstable. So, but nevertheless, physically you say should exist a solution, but I'm pointing out is highly non-trivial. If you give the value of the charges, what are the eta you're talking about is highly non-trivial algebraic problem. As I say, you first linearize it, you find some solution because everything is under your eyes. Indeed, it's linear. When you derive with respect to eta, you know what it is. Yeah. But you see, when you try to compute the next order, of course, you get in a tension of the calculation. Yes. Because the original calculation was really a hard algebraic problem. So this, I think, is the origin of this breaking.
I totally agree with you. It's exactly this point because I couldn't say anything because it's complicated. Yeah. I couldn't say anything sensible about this case. So I just follow the literature and what the type of assumptions that we're making. And my understanding, so maybe I'm wrong, but my understanding of what they did is this. And they reached this conclusion. And to me, it's still confusing because I agree with you that in general, you just need to somehow, you have the next correction, but you just have some more complicated equation for ethers. But in any case, we should be able to somehow prove that it exists a solution, right?
Yeah,
So
this is that part. I agree.
Yes, so that's the part that I don't have any clever answer. So that's why I study just this limited case. But you are absolutely correct. So I totally agree with you. So yes, so it's in this sense that I'm saying that potentially breaks. Yeah. Okay, so, and actually I think in the most recent paper on generalized thermalization, which is into DCFTs, it's actually a PRL by Dimarsky. I think he's saying the same thing as you. But he did in the KDV case, and there's some special assumptions there, which I couldn't do here. But anyway, so yeah, I totally agree with you. This result is very limited. Okay, so in the final part, I'm sorry, I'm running out of time. So can I show this part, Dima? More.
How much time though?
No, I think 5 minutes.
Ah, yeah, sure.
Yes, it's just 2 slides.
Okay.
Okay. So very quickly, so let me just say that this. So the story is how to embed this hierarchy in 3D gravity, and 3D gravity has a formulation in terms of Chern-Simons, and these people here they show how to embed the KDV hierarchy in this paper. So there's some set of boundary conditions that you choose to get this. And then we adapted these conditions to the BO2 hierarchy. But I must say that back then we didn't know the U1 zero modes, so we didn't include this. And just have Einstein-Hilbert with these two U1 currents. And there's some special gauge that you choose in the Chern-Simons. I don't have time to explain, but if you properly choose the chemical potentials in terms of the Hamiltonians, you can get the classical guys, okay? And when you study the potential black hole solutions in this story, they have what we call anisotropic entropy. So the entropy has this form. So the usual CFT would be Z equal to 1. So you have the entropy going with the square root of E, but in general, we have this Z dynamical exponent here. And this type of entropy can be obtained when you study this anisotropic free boson or Lifshitz free boson, which has this action here. So you have a higher derivative in X. You see the Z power over here. And you can actually calculate the partition function exactly like this, and you have this n to the z. And the combinatorial problem related to this partition function is the one of power partitions. So the energy of the states are sum of integers that are equal to some integer n, right? So if you sum a set of integers to some power z, that's your energy, okay? And P of z is for fixed n, how many partitions you have that solve this problem. So this thing here is not known in closed form, even for z equal to 1, although much more is known about z equal to 1. And this story started with works of Hardy and Ramanujan, where they prove a formula when n is very large. So for very large n, you can find an asymptotic formula for this p, and then you can find the entropy taking the log. But actually, when I went to look their paper, the 1918 paper, if you go to the final pages, you can actually find a conjecture for power partitions. So they also have a formula when you have this Z, the same problem here. Although they don't have a complete proof, they have this conjecture, but later some other mathematicians prove this asymptotic formula. And now you have this Z, and it has the same structure that we found from the 3D gravity story. Okay. Although this is just a free boson. Okay. And this part here is related to the vacuum energy. So anyway, and well, and yes, okay, so that's all I have to say. So summary, so we define this GGE of U1 charged to the CFTs using this IFLT basis from the GT correspondence. We calculate the free energy in thermodynamics and the classical limit, included the leading quantum correction. We also obtain the partition function at finite central charge, which relate to partial theta functions. And we studied the generalized charge ETH in the semi-classical limit. And we found this problem that we discussed, that quantum corrections naively break. But of course, I know it's still an open problem. And finally, we discussed how to embed this integrable hierarchy into 3D gravity. And there's a connection with black holes and isotropic field theories. And the perspectives are to analyze the generalized ETH in more details, not just for the charges, but for operators, most simply from the vacuum family, included quantum corrections. And if we are brave enough, we could include finite C terms. And also in principle, the same reasoning of diagonalizing the charges could be applied to the quantum KdV hierarchy. And there is some other story that non-local charges might be relevant. And we also saw that these partial theta functions, so there has some quasi-modular properties that must be interesting to study. And there are also the story that I mentioned of the black hole collapse, the story of thermalization. If you start with a configuration of matter, if somehow we can relate this integrable structure with the collapse. And finally, what I started with discussing these thermalization aspects to see if the results I'm talking about here could be somehow applied maybe to the fractional quantum Hall effect or some other effective field theories in 1D quantum liquids. That's it. Thank you.
Okay. Thanks a lot, Fabio, for the very interesting seminar. Now we have time for questions. Please, if you have any questions, please go on, or if there are more than one, we can use the chat for.
I had one, but if there is someone else, since I've done many.
No, please, Giuseppe, go on. Go on.
Fabio, you know, when you have a usual integrable system, namely conformal field theory is a special case with some features, you can cut essentially all the difficulty of GG going to the mode occupation.
Right, yeah.
Because it's true that if you have the mode occupation, the charges are uniquely determined by it. It's not true the vice versa. And moreover, it's much easier to deal with mode occupation than with these awkward charges. I mean, there are larges and so on and so forth.
Mm-hmm.
I'm not aware of this formulation of conformal field theory. I never studied, I have to confess, but probably you know, you have thought about it. You have the fact that you can reformulate everything really in mode non-trivial, because it's like you have made the transformation to action angle variable, essentially.
Mm.
So it's not trivial, it's not something simple. But if you were able to do it, everything will be solved at once.
Mm. You mean mapping this story of the CFT, the effective field theory, to the story of mode?
Yeah, for instance, imagine you do the exercise of free boson theory. I mean, with mass, just to be safe. So obviously you can compute all these charges and apply to initial configuration of the field, what is the value of the charges.
Mm-hmm.
But this will be tedious in a way. You have to compute the charges, you have to do this. But imagine that you know a priori this mode occupation of the fields. And because you have a initial states, right? So the initial state will be expanded in mode, and you know which mode are going to be occupied.
Mm-hmm.
Since the system is integrable, the mode will be preserved forever.
Mhm.
And so at this point, finished. The role of eta, your infinitely many Lagrange Legendre multiplier, is encoded in the mode occupation at once.
Yeah.
So I don't know if this has been explored in conformal field theory. I mean, actually, it looks pretty strange that has not been done. Actually,
Yeah, I mean, if you're just talking about free bosons or things like
no,
this,
this is simple. This is simple. No, you are
yes.
talking about interacting theory.
Yeah, so when you have the interactions, then the mapping. So you see, you would have something like this, but you also would have some potential, right? Some, well, for some reason it's not. You also have some potential, right? Here.
No, I mean, if the system is integral, you should be able to find the transformation which
Yeah.
lead your Hamiltonian in a free type form with non-trivial epsilon. I mean, is obviously the difficulties in this transformation, which
Yeah.
exists.
Yes.
Time Gordon exists in many other integrable models, but I don't know for conformal field theory. So this is why I'm asking. You see, this transformation is known for many integrable models,
Mm-hmm.
even complicated one. Is this called inverse scattering method? As a matter of fact, is inverse scattering method.
Mm-hmm.
But for conformal field theory, I do not know how it's implemented. But if you were able, you have solved your problem at once.
Mm-hmm. Well, the way I see it is that, so this is the lattice description. And as you said, there are some special potentials that you can do the mapping to this effective field theory description. And this is already the CFT story. So that's what I was trying to say. But in general, you can have uh, terms like this, right? So you can have higher powers, sorry. So what I mean is that you can have a z power of the derivative when you do this mapping, or you can have some more complicated terms. So this is the story that I guess Rodrigo in the audience knows much more
Yeah,
about me.
yeah, I know. This non-linear bosonization stuff like this. Yeah.
Yeah, so, and then you can have terms like this, so cubic in the derivative of phi, but then you do an extra fermionization, then you get a free boson with quadratic dispersion. Oh, sorry, a free fermion with quadratic dispersion, etc. Well, so yeah, so and each of these effective field theories hopefully can be related to CFT or these deformations, because in the way, so in terms of effective field theory, these guys, so you have the CFT Hamiltonian, but these guys can be seen as irrelevant deformations from the CFT fixed point. So there's a, so the mapping should be like this. So somehow you identify the CFT fixed point, what's your energy momentum tensor, and then there are higher terms. But in principle, depending on the system, you can have, for example, T bar, which people are studying a lot now. So this is a type of term that gives an interaction between left and right. So the type of setting that I'm studying, I don't know what to do with this, right? Because now I lose this basis that diagonalizes in each sector. So now the basis mix, and I don't know how to deal with this. So I have to exclude these guys. But every type of system that has an effective field theory description in this class should be related to this problem. And the proposal that I think was Dima that noticed from these papers from Wigman is that, so they noticed that if you want to describe nonlinear effects in the fractional quantum Hall effect, you should study this Benjamin-Ono 2 equation.
Oh, fine. No, Fabian, Fabio, I understood completely. I'm just saying, when you arrive to the point that you know you are dealing with integrable theory, as it is, conformal field theory is integrable just by analyticity. What I'm saying is probably the most convenient way of discussing it is not through the this procedure of going charges, imposing the eta multiplier and this and that, but to try to go at once to the mode occupation of the fields, because these are the ones which are conserved. So I can send you some, I mean, now I don't want to take too long. I can send you some papers on where this story is described is really very, very easy. When you see it, it's immediate to see what's going on.
Okay, thank you. It would be very nice. I mean, I know very little about this story, so I'm not an expert at all. So I'm starting to learn about this. I'm coming from CFT side, trying to understand, let's say, your side or condensed matter side. So if you have anything to help me on this matter, would be great. Thank you.
Any other?
So I may ask a question?
Yeah. Yes.
So yeah, in the meantime, Fabio, can you unshare your screen? I will ask Valdelino to make a picture of people who participate. So everybody who can, please turn on your cameras for us to make a picture for the future memories. Valdelino, please let us know when you are done. So my question is in comparison to the study of KDV. So I understand that your work is generalized on the results in the KDV, but in the end you said that somehow you can use your results to see what how this applies, how this can be reduced to the KDV case. Is there something new in comparison to the KDV case?
Oh yeah, so the works on quantum KDV, they didn't find the explicit basis that diagonalizes the quantum KDV charges because it's a difficult problem. I mean,
wasn't it known from old papers like Bajanov et al.?
No, so yeah, these guys, they don't show this basis, but there's some recent paper by Lukyanov and this other guy that I don't remember that they start to talk about this ODE integrable quantum field theory story, this relationship. And then they discuss, they start to show the first few elements of the basis that diagonalizes the quantum KDV charges. That's the first paper that I saw this. So it seems that Demarsky also noticed this basis, but he only studied in the semi-classical limit. So you see, he writes just the first few terms. So he didn't write, maybe he knows, but he didn't write in the papers the explicit form for this basis. What's special of quantum BO2 is that you can really find explicitly the AFLT, they find these coefficients, right? And from their point of view, introducing the U1 current was just a technical thing. So it's because from the supersymmetric point of view, there is always a U1 part. So they knew they had to have a U1. So that's why they put there. And what I'm doing is that I'm taking this mathematical result and trying to give a physical meaning. That's what I'm trying to do.
Okay, thanks. Yeah, Valdelino informed me that we have the picture already. I have one short question still. Is it clear from your study that the ETH would break once you relax the semi-classical limit? Or you just from the beginning work in this semi-classical approximation and you see it more or less automatically model that discussion that you had, that PTH is satisfied?
Yeah, so for example, I show a case where I have the partition function for finite C, right? If I only put one charge. So in principle, in this example, which I didn't study, I could write the generalized ETH equation, just, but it's in terms of these partial theta functions. So you see, this is already a complicated function. So we need to take the derivative of this complicated function and then try to solve for the chemical potentials, like we were discussing before. So it's like Professor Musardo was saying that you can write the equation, but if you're not clever enough, you don't know if there's a solution. So that's my problem with this. You can write, you can hope there's a solution, but you can only get something concrete if you do some expansion, you know. I guess that's the problem. And I tended to follow the literature that I know from people from AdS3, CFT2, that they reached this conclusion of breaking the semi-classical limit. But again, if you think at finite C and there are the chemical potentials there, in principle, you could find the chemical potentials. But still, there's no theorem, there's no concrete results that I know. So probably.
Indeed, Fabio, you see, when you have one, it's already complicated, as you said.
Yeah.
You have many. The story is not unique one-to-one correspondence. You had it before because you linearized, so one was one-to-one.
Yeah.
But the full problem mixed all the chemical potential with the expectation value of the charges.
Yeah.
So this is the real problem. So as I say, I don't think we'll break anything. It's just mathematical, technical, complicated, but not conceptually, how to say, unstable. I mean, unless you put really instability in the system. I mean, but it's just technical complications, not ontological. How to say? Not inherently. There is no break. I want to say it's not breaking, just technical complications.
Yeah. So I think what complicated the literature is because they started with the usual ETH and they were studying averages of generic observables. And because of conformal symmetry, these matrix elements that we're discussing, they can be fixed in terms of structure constants of CFT. And if you consider primary states and descendants, ETH breaks. It doesn't give the same function. So based on that, they started to study other possibilities. And then they finally enter in the generalized story. And I think in the back of their mind is still these complications that they get. So there's this discussion, if you should include primary states, descendant states. I know, probably the guy that knows better this is Anatoly Dimarsky, professor from Kentucky. So he has this PRL. But I myself, even reading his paper, I'm still confused. So, but probably if you talk to him, he can give better answer. So
he left already, so he didn't participate in the discussion. He left already. I mean, he's not in the audience anymore, so he cannot answer.
Ah, he was here?
Yes, he was.
Ah, okay.
Sorry, can I ask a question, Fabio?
Yeah.
Yeah.
So, so I know that in some cases you have to be very careful when you construct this generalized Gibbs ensemble because they might not be, well, somehow they might not include all the relevant charges that are needed to reproduce, for instance, stationary state, etc.
Right.
And especially you have to be careful because sometimes they are not, you must include also charges which are not integral of some local density. So they are in this sense local. So in your case, how you might be, I think you do not consider this type of object.
So the first question is how many charges should I include, right? So I know there's this discussion in the literature on statistical mechanics, but I don't see exactly, because this is effective field theory description, this is very generic. I'm not thinking about a concrete system, and I don't understand why people say what you're saying. You see?
Because you have other operators which commutes with the Hamiltonian, and they are not built by taking derivative of the transfer matrix, so the logarithm of the transfer matrix when you have some integrable model. So they are not the only charges which appears, the one which obtain taking derivative of the transfer matrix.
Yeah, that's the second part, right? That you mentioned the quasi-local charges in the story. And actually, so in the original Bajanov, Lukianov, Samochkov paper on the integrable structure of 2D CFTs, they say they are the local charges, but they also no local charges. You see, but these guys are much more complicated. They are complicated integrals. So that's why I don't even consider this.
Yeah, but what I'm saying is that you have to be careful, because if you want to match some expectation value and with some result which comes from the GGE, then if you don't include these objects, you might get a wrong answer. Huh?
Yeah, so, but the case that we study in particular is the semi-classical limit, which is people are interested because of black holes. And in this particular case, if you just look for the charges, you don't need these guys. Okay, that's another way to think about the results. So you know there could be no local charges, but in the semi-classical limit, for some reason, it seems to be enough, the local charges. I don't know what's the meaning of this, but so maybe only when you have quantum corrections that you need to consider these guys. But I mean, it's a very interesting question. I don't know the answer. I just know that in the integrable structure of 2D CFTs, you have these guys. And I know that
for sure there are, because it's known, I think, since also paper by Denis Bernard and Leclerc.
Yeah, yeah. No, so the problem is related to the question of Giuseppe, that how to relate the lattice description to the CFT description. That so it's not so easy to go to the long wavelength limit, right? So how do you relate this literature? There's also the story of generalized.
So for instance, if you take XXZ in the gapless regimes, it has been shown that if you include only the charges which comes from the transfer matrix, you don't realize the correct long time limit of, I mean, some
quantum chain, yeah.
Yes, okay. So you have to include also this non-local, then there is all of, there are a lot of names, but somehow they are there. The gap in theories which are gapless, typically there are these non-local objects.
Right, but I would say, I don't know what's the central charge in this case. I don't know much about it. I don't know if it should be C equal to 1 or something
like this, yeah.
So what I'm saying is that if you look at C very large, from the point of view of CFT, it doesn't seem to care. That would be like many fields, okay? So you can have many U1 fields or many free fields, then you can have a very large central charge. So a large N limit or something like this.
Actually, from the conceptual point of view, would be extremely interesting to take an integrable model, which is usual one, say Sine-Gordon, where everything is well known, and then take the massless limit of it. That would be extremely interesting, because you will show that GG will not be braked at all, but also you know how to do the calculation. So that would be extremely interesting calculation to do, actually. Because you come from something absolutely robust where almost everything is known, but going to the massless limit, you recover conformal field theory. At this point, you can compare. I think would be very interesting calculation to do.
Nice. Okay, thank you. Well, I know that Lukyanov is looking at this type of questions, you know, and his approach is different because he used this ODE IQFT correspondence.
I see.
Because he used, in the end, he solved some Schrödinger equation to get the spectrum. So basically, there's some clever way how to find the potential in order to get the spectrum. Instead of diagonalizing the charges, he has this other approach, which I don't completely understand why it works, but it seems to work. And the other comment I had is that in the Bajanov, Lukyanov, Zamolodchikov paper, they define a transfer matrix for SL2, the quantum SL2, right? That's the one that you get the charges that Jacobo was mentioning. So in some limit that they find there, you get the exponential of these local charges. But they also show that there's a different expansion of this transfer matrix that you get related to these non-local charges. So instead of exponential something, you get an infinite sum. And this infinite sum representation is in terms of the eigenvalues of the non-local charges. That's something that I don't understand. But
you are expanding the transfer matter in different limit of the spectral parameter. This is what you are doing.
exactly.
So in some expansion, you see the local charges. In some other, you see the non-local charges.
Yes.
What Jacopo was mentioning is that if you expand another point, they are all conserved, this quantity. You get these crazy semi-local charges. But
Yes.
it's always a unique object, the transfer matter, that is always conserved, depend on lambda, and wherever you expand, you have different set of conserved quantity.
Yes.
This is the story.
So the thing is that in the limit of this parameter that it looks like a GGE, right, exponential of something, you don't get the information from the no-local charges.
It's true.
But if you take another limit, you get the information.
Absolutely.
So somehow the information is there. That's what I'm trying to say. So this should be related to the comment of Jacob, but I don't know how. So this type of limit, there is some relation with this limit of the parameter. You can reinterpret as a semi-classical limit, I think, maybe. Or maybe some high temperature limit, I don't know. So, but I mean, I think that would be the framework. So study this transfer matrix from this paper to understand these questions. But yeah.
Okay, so there are no more questions. So thanks a lot, Fabio, again. Thanks everybody for participating. And hope to see you all next week.
Okay, bye-bye. Ciao, Fabio.
Bye. Bye.
Ciao. Thank you.